everyone, and thank you very much for coming today. I will talk about harm, and the motivation for this talk comes from the now widespread promise or this fuss in the literature about algorithmic decision making, and the idea or the opinion that we more and more will have decision rules that are somehow decided or somehow governed by algorithms, not necessarily with humans in the loop. We can talk about the humans in the loop part also later, but now think about first a setting where algorithms make decisions on behalf of humans. The arguments I'll make will also be relevant to the usual human decision-making case, but the fact that algorithms might take part in decision-making makes us think about some of the principles humans have when they make decisions. And I will focus on medicine, where medical doctors in many countries around the world need to take an oath before start practicing. And that oath is to do no harm. So that seems to be a principle that doctors need to follow in their practice. If we were to algorithmize decision-making, there are now many voices saying that if this is such an important principle to humans, then we might as well try to encode this principle in the algorithm. So if we were to leave the decisions to algorithms, how can we ensure that these algorithms make no harm? So the way to ensure this, or one way to ensure this, is to have some formal definition of what harm is, because algorithms seem to prefer formal statements. And then the question is, how do we define harm? So now, in order to define different notions of harm, I will consider a very simple setting. And it turns out that this simple setting is, if not necessary, very beneficial for certain definitions of harms, but perhaps not others. And I think we might all agree that this simple setting, where we have a binary treatment, a binary outcome, and get local binary counterfactual outcomes, is not covering all the interesting cases. But we'll start there, and we can see that even in this simple setting, we might learn things about how these different notions of harm are related and when they might be different. So the first thing I will introduce is a definition of so-called interventionist harm. So you might always say that I'm really defining nothing here, because the only thing I put up here is a contrast in probabilities, say, of death under treatment versus control. And I'm saying that if this, you can think about this even as an average treatment effect, conditional on some relevant features. And if this treatment effect is positive, in the sense that treatment increases the probability of dying, then we say that the treatment is harmful. Very, very basic. It's just an average treatment effect when we have a binary outcome. And this notion of just contrasting means seems to be the premise for a lot of the literature on optimal decision rules, dynamic treatment regimes. It seems to be the way FDA make decisions as well, in the sense that they approve drugs based on average treatment effect, or sometimes even conditional treatment effects from, say, randomized experiments. But at the same time, there is an increasing literature on a different notion of what is harmful, or a different notion of how we should study whether or not the treatment is beneficial. And this is what is sometimes called counterfactual harm. And the difference here is that here in this binary setting, we are now considering the joint probability that under treatment, the individual will die, and under control, the individual will survive. And if this probability is harmful, if this probability is bigger than zero, then there exist individuals that are harmed. There are some individuals that would die under treatment and survive under no treatment. So the difference here is that this probability statement involves joint counterfactuals under different interventions, so called cross-word counterfactuals. Whereas here we have a contrast of two probability statements that are single word, because they only are defined with respect to one intervention, A equals 1 in this case, and A equals 0 in the other case. So claims about identification of the first estimand can be visualized or described in so-called single-word intervention graphs with all developed by Richardson and Robbins, and is coherent with the theory of FFI CSDG model of Robbins and the decision theoretic framework by Philip David, and is all in a sense interventionist. Whereas this other quantity is not. It involves joint counterfactuals. But before we go into identification at all, I would just look at when does it matter, or does it matter that we distinguish between these two definitions of harm? By the way, this can also be thought of as a probability of causation, which is also an estimate that's been studied for a long time in the causal inference literature. So I'm not doing anything new here. I'm just describing or making, if anything, I'm just giving new names to certain quantities that are already known. But it seems to be given those names in this literature on harm. Okay. And in particular, Julius Pearl, who I suppose many of you know about, has said that this latter definition of harm, this counterfactual definition of harm, provide the key for the next generation of personalized decision making. And he stated that quite vocally in social media and also in papers such as this 2023 paper published in Journal of Causal Inference, and there were also several conference proceedings on this one. And he's not the only one. You see computer scientists in their top venues, such as NeurIPS, promote this type of definition. Social scientists and statisticians, such as the prominent professor Koski Imai at Harvard, does so in legal context. Eddie Ben Michael and co-authors do so in top statistical journals, and an overlapping set of authors also do that in some more recent work, where they claim that this counterfactual definition of harm is crucial for making sane decisions. Okay. So I will start off focusing on some claims by Pearl, because he's influential and he seemed to have been one person who have pushed a lot for this type of notions and definitions of harm. And his claim in particular is that this counterfactual approach is crucial or vital for effective decision-making policies. And counterfactual here means this joint counterfactual, so this last definition I made. I don't want to confuse this with the definition of a counterfactual or potential outcome. When I now talk about counterfactual in these words, it means where we have joint counterfactual. So a probability statement or some kind of functional that involves both outcomes under treatment and control, which we never can observe at the same time. And he strongly objects that a rational decision maker may well apply the interventionist perspective, so the first definition, to the exclusion of these counterfactual considerations. And how did he argue for this? So one thing is just to give these statements in front of you that might somehow be unfair. So in order for me to engage with it, let's see how Pearl, or in this case, Scott Miller, his co-author, and Pearl argued for these claims. And they did so by an example. And this was not a real example. This was an example they deliberately constructed themselves. So now we'll study their example and see, and we can see if we agree about whether or not his claims are true. Okay, and the first part of the example was a randomized controlled experiment. So Pearl gave us these data. He said that suppose I have data from this experiment or randomized controlled trial, where some units are randomly assigned to no treatment and other units are assigned to treatment. And we divide them into men and women. And what you find is that the probability of dying under no treatment is higher than the probability of dying under treatment in both men and women. In fact, the numbers are identical. Exactly the same. So based on these trial results, if that was all we had, and you came to FDA or your doctor with these results, and that was really all you have, because decision makings in practice are rarely made just based on the trial results. There's much more evidence behind it. But suppose that's all you have, then maybe your decision would be, we will give this to both men and women. We won't distinguish between them. Okay. And then Mueller and Pearl said, we have also have access to some additional data. We have data from an observational study. And in this observational study, A is now not randomly assigned. It's the treatment the individuals actually received. So this is the treatment given by the doctor. And instead of looking at what would happen when we intervene to give a particular treatment, now we can just look at what happened when these individuals either received no treatment 0 or treatment 1. What we see is among those who receive no treatment, the results are the same in men and women. But among those who receive treatment, the probability of dying is substantially higher among women than among men. Okay. We can go and make one table where we include all of these numbers together, and then make one for men and one for women. And the first row is just the result from the randomized experiment, where you see the results are identical. And we see that for the observational study, there is one entry which is different between men and women. Okay, and based on these data, Pearl correctly calculated that the probability of counterfactual harm in men is actually 21%, but there's no probability of counterfactual harm in women. So he was puzzled by this, it seemed like, because as he said, as an interventionist, you would just contrast these expectations. And you would say the contrast of expectations is the same in men as it is in women, thus we should give the same treatment to men and women. However, when I look at this probability of harm, there is a substantially larger probability of harm in women than there is in men than there is in women. Yeah.
I can see that 21% is a maximum possible value for that. But yeah. But that says equals. Where are these numbers coming from?
Yeah, so that's part of the mystery here. But if the maximum is equal to the minimum, do you agree that's 21%?
Well, yes.
Yeah. So in this case, the maximum appears to be equal to the minimum. And then the other question you can ask, how could he possibly point identify this quantity, because it involves joint counterfactuals based on these data?
Whereas I can understand why the maximum would be 21%. Why should I think the minimum is 21%?
In general, you should never think that. But there's something about the construction of the example. So we'll get to that.
Okay.
Because in general, this quantity will not be point identified. Mm-hmm. But in this case, it happens to be. But this is a construction. I said that Pearl constructed this example. So I'm not going to talk even about identification in the first slide. So take that as a face value, and we'll get there, because you're one step ahead in terms of identification.
Okay.
But let's just say that he was right, and he could get there. Okay? And he was, but they were right in this case. And the conclusion is, paradoxically, the interventional framework would judge the two treatments as equally efficacious, merely because the death counts for both treatments are the same. So that's the first row. But the counterfactualists wouldn't. So he further says counterfactual considerations can save life on both fronts. It cautions against treating those who could be harmed, in this case men, and it provides a green light to treat those who are safe from harm, in this case women. So this is his conclusion from the example. Okay? So now I will say that I think this analysis is flawed. And for several reasons. But the first reason, it's not about their computations being wrong, but it's about other things. So when they did their combine the trial and the observational data, they did so only in their counterfactual analysis. This is an important mistake, because the observational data were not used in the dimensionist analysis. That's the whole point. So this should be a not. They only used the RCT data in interventional analysis, because the interventional analysis for him was just the contrast of the outcomes in the RCT, what you saw in the randomized controlled experiment. So scratch that observational data. But in the counterfactual analysis, he deliberately used data from both the trial and the observational study. So he's using different type of information. If you use different type of information, how can you compare? Okay. So in other words, he only used this white row, the upper row, in the interventional analysis. He combined both rows when he did the counterfactual analysis. And we'll see now why that can resolve all his possible contradictions and all the reasons why he claimed that the counterfactual rule is better than the observational. Okay. And the way we'll go with that is to use the so-called natural treatment value. So think about, I call it here, to be very explicit, I call it A star. And the notion of a natural treatment value dates back in the literature to several works by Jamie Robbins. It's also used in identification of the so-called average treatment effect of the treated, which will come in here as well. Other prominent people in the field have also worked at this, so including Pearl, also Philip David, and others. Okay, so this is like a basic quantity to study. But the point is that this natural treatment value is equal to what people naturally do when it's not in an experiment. So if we are in the observed data, we can think about this A star as just being A, what's given. So if the doctor gives treatment, that's their natural decision, you see it. But if you are in the experiment, in the RCT, you don't know what this natural treatment value is, because the treatment is not assigned by the doctor anymore. It's just assigned by the random number generator. Okay, so that's why when you have the observational data on top of the trial, you get access to this natural treatment value. So let's take a table here. And my first claim is that had we only had access to the experimental data, then, and I'm not showing you all the calculations, but Mueller and Pearl would never be able to say anything precise about this quantity. So they would be uncertain about whether this treatment is harmful or not. Their bounds would be uninformative. It's true still that from the interventionist notion of harm, they would say that the treatment is not harmful because it actually reduces the probability of death. So in that interventionist sense, that treatment reduces mortality, and thus they would say this is maybe the right thing to do, if that was all they used for decision making. But the interventionists could not say anything about these specific quantities when we condition on the natural treatment value, because the natural treatment value is not available. They don't measure it in the experiment. What Pearl did was that he compared results when he had experimental and observational data when he studied the counterfactual harm, because it turns out when he combines those data, he would be able to get to these numbers. Remember the two tables with men and women I showed? This was two by two tables, so 8 entries. He used all of them to get to the conclusion that the treatments were harmful. And if had we used all of these data in the interventionist analysis, we would not get to the conclusion that the treatment is overall not harmful. We would find that it is actually harmful in those who decided that they did not want the treatment, or those individuals that the doctor decided should not receive the treatment, where the natural treatment value is not treat. So the doctors had a good intuition. But it would be desirable or non-harmful in those individuals the doctor decided to treat. So as soon as we use the relevant covariate, the A star, the doctor's intuition, if you want, then there is no contradiction. So as soon as you use both the experimental and observational data in both settings, Pearl's claims become moot. It's just because he was doing an analysis where he used much more information to make one claim than the other. And we can even go further and say that Pearl actually didn't use all the information he had access to. He didn't leverage his information well enough, because he could also make these counterfactual harm statements conditional on the natural treatment value. In our setting, we could even distinguish, as an interventionist, you could distinguish between those that naturally the doctor would like to treat versus not treat, and you can see that the doctor had good intuition. These shouldn't be treated, but whereas these people should be treated. Okay, I put an NA here, and this is because if you really want to make a decision based on the relevant covariates, you should use that covariate. So I put in an NA in the sense that if you did not have access to the natural treatment value, all you might base your decision on is this mean outcome. But if you do have access to it, you better use it, and you know that's why I put in an NA. So to be very, very clear, Pearl didn't have the imagination, I believe, to include quantities conditional on A star, the natural treatment values in his own analysis. And had he done that, he could get as sharp conclusions as you can get as an interventionist. And in fact, they turn out to agree exactly. So all the claims about contradictions and all the claims about these things not adding up, they're not true if you use the same type of information. Which is shown by these entries, no yes and no yes here. So in this case, there's no disagreement between the two definitions. And our point is that if you only rely on assumptions that are in principle testable in an experiment, where you combine also observational data, if that's all you rely on, you will not get to these contradictions. So the settings where you get to contradictions are precisely where you have asymmetric information, and you rely on untestable assumptions on top of those you have in the experiment. So at that point, I think the results should be, that claim should be clear. And this is also here I cite work I've been involved in. Philip David and Stephen Sen has written a related paper that come to the same conclusions as ours, which will soon appear in observational study with the discussion. Okay, so here's what I said. Counterfactual analysis will detect harm exactly when an intervention is due if they rely on the same type of information, in the sense that if they rely on comparable information that is and assumptions that are guaranteed to hold by design in the experiment. In that sense, we don't need that counterfactual logic that Pearl claimed we need.
Yeah. Sorry, Matt. Just that. Does Pearl accept this point that it was only based on using different information that you got to so-called different conclusions?
So so this is based, I should say, Pearl wrote with Mueller a commentary to this paper, and then we wrote a rebuttal. And in the rebuttal, we showed all of this, and he hasn't responded.
Okay. Right.
So you take that. I was supposed to discuss this with the American Causal Inference meeting in a couple of weeks, and the co-author would be there. Sadly, I can't go. So let's see what they say after the meeting.
When you say a counterfactual analysis detects harm,
Yeah. So in the sense that they find
there are three possibilities on that. One is the analysis shows that there is harm.
Yeah.
Another is it shows that there isn't harm. And another one is that you don't know. So when you say detects harm, you mean
that there's a yes here. In this case, it's only about identification because Pearl doesn't do much estimation anyway. So what they do is that they they imagine large data. There's no statistical uncertainty.
Right.
And then we can point that we can show inequalities. There are inequality constraints saying that this quantity needs to be bigger than 0. So detecting harm means that this is not a probability zero event.
Yes, okay.
But it is a probability zero event in certain subgroups, and Pearl didn't know that. So it's entirely safe to treat men that by the doctor were recommended to take treatment.
Right.
So that says a lot. So now I haven't talked about identification here. You asked a question about it, but I've now compared them just on decision theoretic equivalence. And we'll continue a little bit with that before we go further. So if you further want to use this for an algorithm, say, to make decisions, maybe you want to rely on some basic decision theory. And the only thing I will study here is, like, suppose you want to maximize some utility, call it UG, where G indicates the decision rule or regime. So this is again a counterfactual. So utility under, say, treatment versus control. That's what indicated by G. There's nothing deep or new here. At least I'm not adding anything deep or new. This is just very basic decision theory. Okay. And a counterfactualist would say, we have the following 4 objects. We have the doomed individuals, those who die regardless of treatment. We have the immune individuals, those who would survive regardless of treatment. We have those individuals that only die under control or no treatment, or those are helped, and we might have some harm. Okay? And they will then, in order to come to different conclusions, I'm saying this hand wavy, but this is effectively what's happened. In what they often make as a point for using all of these principal strata. So first of all, in order to come to a conclusion that's different from an interventionist, they would often say something like, oh, it's worse to treat someone who is harmed than not to treat someone who is helped. So this is this idea that an error of commission is worse than an error of omission. So obviously this depends entirely on the coding of treatment. What is A is equal to 1 and A is equal to 0, and probably depends on the setting as well. If you compare 2 active treatments, it's not clear to me what this really means. But they have this idea that they claim that this is worse. Okay, we can take that as face value. If this is the best way of encoding or not, we can still discuss later on. But this is a claim often made. So they will then create a utility function. So this is just one utility function. That's why it's indicated by 1. That's a function of the treatment given and the joint counterfactual outcomes, those unobservable quantities. What would happen under treatment and control. And by the way, you should think about this if you go beyond the binary setting, this becomes even more messy. But as an interventionist, you don't need to deal with it, but the counterfactualists probably do. But they've decided to study this setting. Okay. And they would simply say, if they have defined this utility, when treatment A is assigned, A equals 1 is assigned, and that has actually lower utility than assigning no treatment, that's a bad idea. Okay? Whereas for an interventionist, it's simpler in the sense that they would usually consider this, or they would consider decision rules that are some function of the treatment received and the outcome they expected under that treatment. So only the A here and the A in the superscript always match compared to the A here, which will mismatch with at least one of them. So it's not a single word quantity anymore. So this is the difference, basically, if you describe this in terms of utility. Nothing deep. And in this case, they will, I messed up the inequality here, I'm sorry, but they would, when treatment is harmful when the utility is lower under treatment versus control. So this is correct. Okay. And just to make a very basic point here. So suppose you want a treatment that maximizes survival, which is the same as minimizing death. Then an interventionist simply just chooses the treatment that minimizes the expected probability of dying or maximizes the survival. That's what they do. It's designed to optimize for that. So if that is your aim, you know, and this is in some sense circular, because this is, if the idea is to maximize survival under one treatment regime, then the interventionist decision criterion is precisely defined to maximize the utility in that way in the signal world. So then you will get to that decision. I'm saying this point just to say that whenever the interventionist utility is different from the counterfactual utility, and that materializes in different decision rules, then you know that the rule that uses the interventionist utility will maximize survival, and the counterfactual will not. So in that sense, if you prescribe to this counterfactual decision rule and all you care about survival, and of course we can add in a cost of the drug and all of these things too in the interventionist framework, but if you really are concerned about getting the best outcomes under the decision rule you want, in the sense that maximizing some single word quantity, that is what the interventionists are doing. And this seems to be the way drugs are approved. This seems also to be the way I think doctors and patients think when they make decisions. So you should just know that if you don't prescribe to that, then you have to accept that more people will die under the counterfactual decision. So in order to have a principled debate about these notions of harm, I think the first question we should ask is that do these formalizations correspond to the notions and beliefs and intuitive feelings we have about harm that we want to encode? That's the first principle. We have to translate the question or some features into a formal estimate. And if you want to compare different definitions, we should also see what are the consequences of implementing them. And in our case, we could at least clarify that in Pearl's claimed contradictory scenario, where the actual notions of harm would dramatically change personalized medicine. We show that that's not necessarily the case. But we cannot only look at 1 and 2. We also need to look at how can we operationalize or use these definitions, because it's easy to come up with a definition, but if we cannot use them in practice or even identify the estimates, it's perhaps hard to see how they can be useful. And if you go back here to 2000, but there's also a much older literature on probability of causation that I alluded to even earlier in this talk, because this probability of harm is just precisely a probability of causation. It's a probability that the treatment causes harm or causes death in my example. And people have known and studied these type of objects for a long time. And if you go even back to the old statistics in legal practice literature, Sander Greenland and Jamie Robbins wrote that the usage is a misapplication of epidemiology, because it's been shown that without imposing restrictive biological assumptions, epidemiology cannot supply estimates of the probability of causation. Okay? So in some sense, I'm saying nothing new. This has been known for a long time. It's just been reframed and rephrased. But how could the probability of counterfactual harm be pointed at in Mueller and Pearl's example? What happened? This was basically related to your question. How could we get to this probability of 0.21? This was because there were certain determinisms in the example that were not visible from the two by two tables I showed you. But if you had used this natural treatment value, you would see that some of the distributions were degenerate. Okay, and this is probably the case whenever the probability of counterfactual harm is identified, because usually it's not. We know it's only bounded. So the example was constructed to point identify these quantities. And I'm not blaming them for doing that. That's fair. They can do that. And they even say that in a later iteration because they received some comments on it. But you should also know that even identifying this quantity is in general problematic. You only get bounds with single word assumptions. This was not, they know this because Pearl and others have derived bounds on similar quantities and studied them for a long time. So this is not new to them. It's just that there's some selective information in the presentation of these results. But this is a second argument on top of all the other arguments I gave so far, which already apply regardless of this is point identified or not. If you want to read more about these things, you would maybe be entertained by this back and forth where my colleague Aaron Sarvet, now an assistant professor at UMass Amherst, and I wrote a paper. Then Scott, Mueller and Pearl replied. It's also published in the American Journal of Epidemiology. And then we wrote a rejoinder with many of the points I presented here. Okay. You should also see some recent and related work by Philip David and Stephen Sen, which will soon appear in observational studies. Okay. But I also want to go one step further because this was a toy setting in the sense that it was a simple setting with a binary outcome and binary treatment. And in practice, there might be outcomes that take more than two possible values, and often we are faced with more than two possible treatment values. And in those settings, the counterfactual harm criterion has additional problems. For the interventionist one, you should intuitively see that it shouldn't necessarily be a problem. If I have more treatments or I even a continuous outcome, it doesn't make a problem. I just choose the outcome that seems to be, if one improves quality of life more than all the others, I will choose that one. But if you have these joint statements where you need to look at the joint probability over many different treatment and outcomes, that becomes more difficult. So this is some intuition you can have. But in order to talk about a particular one, I'll talk about intransitivity. So intransitivity is known to many of you, but I'll just illustrate it in a very simple example that was given to me by my former PhD student, Amit Sawant, now a postdoc, who came up with the idea of all the results I will show here now, after we were discussing harm. So this I attribute to him. And imagine that you are going to a restaurant, and the first you hear is that you're given a choice between fish and meat, and you choose fish. But then they say, oh, sorry, we actually just have meat and veggie. And then you say, oh, but then I would choose meat. Okay? But they say, sorry, again, we mixed up completely. We only have veggie and fish, and then you choose vegetarian. Okay? Is this person I'm referring to irrational? Well, according to basic decision theory, yes, because there's a intransitive order here. You choose fish over meat and meat over vegetarian, but all of a sudden you should choose vegetarian over fish. And this violates one of the axioms of von Neumann and Morgenstern's decision, basic stuff. Okay. And now we'll show that Pearl's decision criterion, or the counterfactual decision criterion, is intransitive as soon as you have more than two treatments and outcomes. And we can do that in a very simple example, and I attribute that also to Amit Sawant. Okay. So just for the sake of it, suppose that we have an outcome that could take 6 levels that are ordered, 1 to 6. And we have 3 possible treatments. And I will illustrate this with pies. And pie charts are kind of abandoned in Stats 101 courses, but here I think these are the best ones to illustrate these things. And you can see if you agree. So imagine that higher levels are good. So in this setting, these are the outcomes under treatment A is equal to 1. These are the outcomes under treatment A is equal to 0. And these are the outcomes under A is equal to 2, and these are the outcomes under A equals to 3. And in each of these cases, you will see that the second pi is preferred over the first one. But the third pi is preferred over the second one. But it turns out the first pi is also preferred over the third one. So you have this intransitive cycle. You will choose treatment 2 over treatment 1. You would choose treatment 3 over treatment 2. But then you would choose treatment 1 over treatment 3. So if you were to apply blindly his binary decision rule or their binary decision rule to this setting, you will come to an intransitive conclusion if you did pairwise comparison.
Sorry. In the construction of your example here, y1 to 6.
Yeah.
Y2 is better than y1, but are they ordinal? So the step between y1 to y3 is the same as y3 to y5. Is that implicit in your construction?
Sorry, that the step from y1 to y3.
Is the step from yi to yi plus 1 constant?
Yeah.
That's implicit.
So this is implicit when you have an ordering, because his statement is all about, it's not about the magnitude, then you need to put the utility to it. So here's just an order. So as soon as one outcome is better than the other, it's better. And everything will be solved if you put in utilities, as you're saying. But they're not. Because they're just talking about the probability of causation being worse or better. So as soon as you do that, you're good. So your answer is correct. But that's not what they do when they define it. So you can solve it in that way. And the interventionist is ultimately doing that. They have to put in a utility and then everything becomes transitive.
You say one better than A3?
Because A4 is dominating 4 is dominating 3 in a substantial mass that's bigger than 0.5.
Weighted average.
It's in the weighted average. So you put this pi on top of each other and you look at the mass where this one dominates the other one.
Do you mean that A1 has a higher mean?
No, you look at the if you put these on top of each other, you look at the area where y4 is covering y3. And then you can rotate them as well. And maybe it's, do you see? So like on the individual level, you don't know if those who have y1 here would be in the y6 or in the y3 group. But you can do worst and best comparisons. And then you can get to bounds and you'll see that.
Oh, I see. So there are some people who, when they get A3, they get an outcome of 6, y6. And that's better than anything you can get with A1.
Wow.
But because that's only a small proportion of patients.
That K portion, right? Which is something like a fourth or less of the circle.
Okay, because I'm not sure you spelt out what rule you're using to decide what.
So you have to get balance, because this is one single world. But what you know from this pi is that, say this is 1/6 of the population.
Yeah.
And that 1/6 of the population get the worst outcome, the rest got the fourth ordered outcome.
Yeah.
And you don't know what these people will get under A is equal to 3.
Mm-hmm.
But you can, but in one, the most extreme case is that all of them get y6. The other case is that all of them get y3. These are the two extremes.
Yeah.
Then you map them to each other and you find that. In either case, a lot of people, in fact, more than 50% will have their outcome y4, which is better than the y3.
Right, it's because of more than 50%. Okay. Right.
And in that case, that's the preferable rule if you just base it on ordering.
Okay. Thank you.
Okay, so to wrap this up, we can figure out when the counterfactual and interventionist decision rules or harm criteria coincide. And in the case of a binary treatment, we can write that very explicitly, and the binary case is the one that's been most studied in this literature. And when they give different answers, we know that the interventionist criteria is by design the one that maximizes survival. So if that's what you want, you should just stick to it, but it's in some sense circular because that's what it's defined to do. The interventionist criterion also by construction requires less stringent identification assumptions because it's a single word quantity, is something that's in principle verifiable in an experiment. And it's so that they're amenable to empirical tests and something that correspond to what we will find, say, in a randomized experiment. And it's also straightforward to deal with non-binary outcomes and also non-binary treatments. But if you are a counterfactualist, you need to think carefully about these intransitivities. You also need to think carefully about how you would express kind of thing. So if you want to see some papers that I based these presentations on, there were these two papers in the American Journal of Epidemiology. Here's a preprint, but it's now published. And this intransitive argument is something we just wrote up as a small piece recently. But this is also related more broadly to how to make decision rules that are functions of natural treatment values, what doctors naturally do. And this is very interesting because it opens up a lot of interesting methodological work and some new conceptual ideas where we need to identify such regimes that are functional natural treatment values. And this builds heavily on the results on single world intervention graphs by Richardson and Robbins from 2013, where really they lay the foundation for this type of theory. We show even when there's unrestricted confounding, you can actually leverage these ideas to get new optimality results. So I stop there. If there are any questions, I'm happy to take them.